Recording, got audio, excellent. All right. Get rid of all this. What number was that problem? 24. Okay, a length of aluminum wire is connected to a precision 10 volt, 10.00 volt power supply. Four significant digits. And a current of 421.2 milliamps is precisely measured get that right, 421.2? At 23.5 degrees C. The wire is moved to a new environment of unknown temperature where the measured current is now 0.3818 amps. .3818, is that right? Got it. Okay. And the wire is aluminum. So, where is our, and they want us to measure they want to know the new temperature. So where is our chart? Right here. No, we actually would do. That's aluminum, 2.65 times 10 to the minus 8. At what temperature? No. 2.65 times 10 to the minus 8 is at 20 degrees. And its temperature coefficient, alpha, is 0.00429. Per degree C. Now, what is our resistance at 23.5 degrees C? I is E over R, so 10.00 volts divided by 0.4212 amps. So to 4 significant digits, what is our resistance? Say again? 23.74 ohms. Is that what everyone else gets? Okay. All right. That is our resistance at 23.5 degrees C. How much will that resistance change if we go up or down a degree C? Well, what we're looking for is a new temperature. But we know that the voltage at the new temperature is going to be 10 volts. But now the current is going to be 0.3818 amps. So what is the resistance at this new temperature? I need 4 digits. 26.20 ohms. So the temperature went up, and the resistance went up by 2 or 3 degrees, or 2 or 3 ohms. So how does the equation, how does that? Right, but we don't really need to worry about resistivity. I know I said we would, but I was wrong. We're going to remember the resistivity times the area divided by the length gives you your resistance. So if you take your resistivity equation and you just multiply by area over length, multiply through by area over length, and it changes it from resistivity to resistance. So we've got R naught times 1 plus alpha times T minus T naught. Now, T minus T naught is simply your change in temperature, your delta T. Okay? So what this equation is saying is that for this many degrees, this much change in temperature, this many degrees C, it's going to change your resistance by this much per degree C. Okay. So, now we've got at 23.5 degrees C, we have an initial resistance of 23.74 ohms. We've got alpha is what? I thought I wrote that down. So there it is. And our T naught is 23.5 degrees C. All of that is equal to our final resistance, which is 26.2 degrees. I mean, not degrees, ohms. Okay? And now we just solve for T. Well, let's start by dividing both sides by 23.74 ohms. What's 26.2 divided by 23.74? 4 digits. We left with 1.103. And let's go ahead and keep some extra digits. Just for good measure, we can round down to the correct number of digits at the end. That is equal to 1 plus 0.00429 times T minus 23.5 degrees C. So next thing we're going to do. Well, how about we just subtract 1 from both sides? And then we end up with 0.1036226 is equal to 0.00429 times T minus 23.5 degrees C. And now we can divide both sides by alpha there, by 0.00429. We're left with 24.15 is equal to T minus 23.5 degrees C. Oh, and for the record, what was the units of this 0.00429? 1 over degrees C. So when we divide by 1 over degrees C, we end up with 24.15 degrees C is equal to T minus 23.5 degrees C. So if we add 23.5 to both sides, what's 2415 plus 23.5? 47.65. But wait, do we have 23.5 or 23.50? Was the stated temperature. So we've got 3 significant digits. We end up with 47.7 degrees C is the final temperature. Everybody see how that one was done? You're going to be able to do it again whenever it's on an exam. I tell you what, I could stay caught up with my work a whole lot better if I didn't let y'all come to class. Every week y'all come to class and I'm behind again. It's a joke. No, that was a joke. Sometimes I feel like that commercial back in the 80s about, I don't know if y'all remember a movie back in the 50s or 60s about some wonderful world of Susie Wong or something like that. It was a William Holden movie. Anyway, there was this actress, this Oriental actress who played Susie Wong. That, as far as I know, was the only movie she ever made. But then in the late 70s or early 80s, she did an infomercial for this product, as seen on TV product called Pearl Cream. It's supposed to be like an anti-aging cold cream for women or whatever. But when they introduced her as a famous actress. At which point I remember thinking to myself, if you have to tell me that she's famous, she ain't. And that's kind of how I feel sometimes. If I have to tell y'all it was a joke, y'all ain't laughing, obviously it wasn't. Do we have any more questions from the homework, the assignments? Oh, you know what? I didn't bring the folder. I've got homework and exams and stuff to hand back to y'all. Remind me after class. Any of you really in a hurry for it to get it back? Okay. Then I'll get it back to you. Do we have any more questions before we go on? Yep. Nope. Well, then let's talk about electric power. What is an EV? An electron volt. It's a unit of what? No. It very conveniently converts to a voltage, but it is, how do you convert it? An EV is a unit of energy, and it converts to joules. And remember, when you have your, you know the mass and the velocity of the particle, then that you can calculate the kinetic energy in joules. There's 1.6022 times 10 to the minus 19 joules per electron volt. So an electron volt is a unit of energy. It is charge times voltage, which is coulombs times voltage gives you joules. That means you can define a volt in terms of units as joules per coulomb. Right? And that gives you, that means that when you then multiply charge, Q times voltage, that gives you units of energy. So what then is power? Let me state this differently. What's the difference between talking about the energy of something and the power of something? How much energy does it take to lift your car up off the ground? Okay. Can you lift your car up off the ground? Oh, but you do. You can and do. You have a jack. You jack up your car. And you lift it off the ground. But you only lift it a little bit at a time. Okay? So, the difference between energy and power is how much time you take. Stated differently, power is energy expended per unit time. So if you want to raise your car off the ground, you can do it with a bumper jack. If you want to raise your car off the ground in half a second, it's going to take more than you've got. You're going to need something else to provide the power to do it. You can provide that much energy, but you can't provide that much energy that quickly. In an electrical circuit, when we're talking about electricity, what are the units of power? Say again? Watts. Thank you. Power defined in units of watts. And a watt is what? A joule, 1 joule, it's units of joules per second. Okay? Well, if the energy in power is Q times is charge times voltage, what is charge per delta T, per unit time? Coulombs per second. Charge per unit time. What are coulombs per second? Like if you had, say, 6.24 times 10 to the 18 electrons worth of charge passing a given point in a wire every second. Current, thank you. Q per unit time is current in units of amps. So that's this. That means your power is actually equal to current times voltage. How many of you have actually seen that written that way? Power, watts. I.e. E is electromotive force or voltage. I remember that? That's watts. Of course, E is equal to I times R, right? So you could write that as I squared R. Or I is equal to E over R. So you could write this as E over R times E, or E squared over R. All three the same basic equation, just changed up. So how much power is dissipated in your circuit? And what does that mean? You build a circuit. You've got a resistor that has so much current flowing through it. It's dropping so many volts across it at that current. That means it's dissipating a quarter watt, a half watt, 1 watt, whatever. What does that mean when you say that that resistor is dissipating 1 watt? It means that it is dissipating 1 joule of energy every second. How many of you ever did you pay your own electric bills? What do they, when you get your electric bill, what do they bill you for? No. They bill you for kilowatt hours. Power times time. See, they don't really care how fast you use it. They just care how much energy did you use. And they get how much energy you use, how many joules of energy you end up using by the number of watts you use per hour or for every hour. So if you're using 5 watts for 1 hour, that's 5 times 60 minutes or 3,600 seconds. That's 15,000 joules of energy that you're using. Now, of course, they don't use watts, they use 1,000 watts or kilowatts. And they don't use seconds, they use hours. But it's still the same thing. They're multiplying power times time to go back from joules per energy per unit time times time brings you back to the total amount of energy that you used. That makes sense to everybody? All right. So you got a headlamp for your car or truck. Example in the book. Let's work it. Got a headlamp for your truck. It is a 40-watt lamp. What's the resistance of that lamp, that headlight bulb? The electrical resistance. You know it's 40 watts. You know it's built for your truck, so it's your truck, I'm assuming your truck is a 12-volt system. So it's made to hook up to 12 volts. Divided by R gives you 40 watts. 12 volts squared, that's 144 square volts divided by R is equal to 40 watts. Multiply both sides by R and divide both sides by 40. You get the resistance is equal to 144 divided by 40. It's 100. Somebody with a calculator, give me a number. .6 ohms. Anybody get a different number? Oh yeah, it's right here in the book. They worked it out for us. All right. Here's a good one. Have you ever done the, and I don't know if you've ever done this. Have you ever actually gone and calculated how much is it going to cost you to leave something running? All right. Let's work through this problem because this is actually handy to do. You think about, you think about saving energy when you get concerned about how much your electric bill is going to cost, and you think, well, I'll turn out some lights and that'll save some money. How much money does it actually save? Let's start by working through the example here. 18.9 of an electric heater. It's 15 amps on a 120 volt line. This is the electric heater draws a steady 15.0 amps on a 120 volt line. how much power does it require, and how much does it cost per month, that's for 30 days, if you operate it 3 hours per day. And the electric company charges 9.2 cents per kilowatt hour, which is actually pretty close to about what they charge around here, is what they charge me. So, 15 amps times 120 volts. Who's got their calculator out? Or 1.8 kilowatts, right? So, if you run it for 3 hours a day, that's 1.8 kilowatts times 3 hours is how many kilowatt hours? $5.4 kilowatt hours per day. Multiply that by 30 days. $162 kilowatt hours. Times that times 9.2 cents or 0.092 0.092 times 162. How much? So 15 bucks to run that electric heater 3 hours a day for 30 days. But it's an 1800 watt device. What if you wanted to run a 100 watt light bulb, or let's say a 50 watt light bulb on your front porch, and you wanted to run it 12 hours a day, so it stayed on all night? Oh, it's a 50 watt bulb, so 50 watts times 12 hours is how many watt hours? Say again? 600? So it's 0.6 kilowatt hours per day. You multiply that times 30 days. $18 kilowatt hours. $1.70 to run that bulb 12 hours a day, every day, the whole month. Less than $2. Now, you want to scare yourself? In my house, I've got all of my system, my central air and heat are heat pumps. Went all electric as soon as I got here, because propane was natural gas, propane, whatever they sell to put in those big silver pill-looking tanks. That was costing me a lot of money to keep that thing filled. Oh, much more. Yeah. So I went to all electric. And I had my central air heat and air units changed out to heat pumps. And that saves a lot of money. It also saves me a lot of money because I've got a fireplace that's actually tied into the ducts. So when I'm burning a fire during the winter, that fireplace cuts easily $200 a month off of my electric bill every month, all winter long. But here's a caveat: heat pumps are extremely efficient, very, very economical, but they're only good to a certain delta T. When it gets too cold outside, they just can't keep up on the inside. They can't maintain that great of a delta T, more than like, I don't know, 40 or 50 degrees, something like that. So, if you got it set to 70 degrees inside, it gets down to 20, 15, down into the teens outside. It's not going to be able to maintain that 70 degrees. So you're either going to crank it down to 60 degrees and wrap and bundle up, or more likely there's what's called an emergency heating element that will kick on in the plenum and heat the air to pump it to blow through the house. It is a 30 kilowatt device. Yeah, ooh, it's right. 30 kilowatts. Now, what happens if that thing has to start kicking on and it runs for, over the course of the night, 4 hours? What's 30 times 4? 120 kilowatt hours for one night. That's assuming that it only runs for 4 hours when it kicks on. No, just for the one night. What's that? 9 times 10 cents. $12 an hour. That's $12 a night. That one night, it gets cold enough for that thing to kick in, and you just spend as much as you would to run a space heater 4 hours a night for the whole month. And when's the last time it only got that cold once? Fact is, if it gets that cold for 3 or 4 nights in a row, or in 1 month, then that heat pump, that emergency heating element can very quickly run your electric bill up another $100. Point is, it's amazing to me how few people actually go through and calculate how much are you going to save, and where do you actually save money, and how much do things actually cost you. Okay, why don't we do this one? I don't know that I've ever done it before. Let's work through 1810. Lightning is a spectacular example of electric current in a natural phenomenon. And there's much variability to lightning bolts, but a typical event might transfer 10 to the power of 9 joules of energy across a potential difference of perhaps 5 times 10 to the 7 volts during a time interval of about 200 milliseconds. Okay, well, first of all, I guess since we don't really have any way of knowing about how many joules of energy would be involved, then we're gonna go with their numbers. But just for our benefit, look at that picture of that lightning bolt. How long is that arc? Just rough ballpark guess. How long? About how many meters do you think that lightning bolt is? 200 meters? That's 200 feet up? Okay. Somebody else? It's like, yeah, 600 feet. Couple thousand meters? 500 meters. Okay. So you're about 75 meters to. Let's just. Well, let's make it easy. Let's say, let's guess that it's 100 meters. Just because we need a number, and that's a nice, easy, round number to work with. What did we say the breakdown voltage of air is? 3 million volts per meter. The exact number doesn't really matter. Just round out, we're just order of magnitude guesstimating here. 3 million volts per meter times 100 meters. How many volts would that be? That'd be 300 million volts. That's, they're saying a potential difference of about 50 million volts in a lightning bolt. 5 times 10 to the 7 volts. That would be 50 million. That means they're saying, I guess that means they're saying that lightning bolt would be about what? Well, we'll get there, but that will depend on the joules and the time, how long the bolt of lightning lasts. Yeah, they're saying that's about 1/6 of as long. So in other words, we were estimating at 100 meters, we would be estimating that it's about 5 or 6 times as long as they say. That's fine. All right, well, what is the total amount of charge transferred between the cloud and the ground, and what is the current in the lightning bolt and the average power delivered over the 0.2 seconds? Okay, well, let's say estimate the charge, Q, that's transferred as the potential energy change. The potential times the charge, the delta V, the change in potential times the charge. So the change in potential energy is 10 to the 9 joules, they said. Divide that by the delta V of 50 million volts, and that gives you 20 coulombs of charge that's transferred in that bolt of lightning. So now, if it takes 0.2 of a second, or 200 milliseconds, 20 coulombs divided by 0.2 seconds, that lightning bolt, then they're saying, is about 100 amps. And the total energy dissipated divided by the time that it took, you end up with, like I said, 5 gigawatts. And then they do it in a different way with just power times current times voltage, which is already estimated at 100 amps, 50 million volts, and that's 5 gigawatts. happen. Not the only time it's going to happen is if God just doesn't want you dead yet. But yeah. Yeah. Y'all work in the high voltage stuff, construction area over there, right? No? Yeah. You ever see someone that's been hit by, and forget about a lightning bolt, just a power line, high voltage power line? Seen pictures of it? It's literally, you literally internally cook the flesh of the person. It's burn. It is a thermal burning. It's not, yeah, it is not something you would want to survive. Yeah, I mean, seriously, I used to, before in a previous lifetime, as they say, many years ago, I was a supervisor for an alarm system company. Did electronic surveillance, access control, alarm systems, things like that. And I went into one of our accounts where one of my predecessors had done the installation. And instead of having the electricians put in a receptacle so he could plug in our little, those little black transformer blocks that you can plug right into the outlet. He'd taken, you know what zip wire is, brown zip cord? Like this wire right here. He'd taken some of that and run it over and stuck the bare ends of the wires, stabbed them into the blades on the breaker pan on a 600 volt power distribution. I saw that and just said, stop, everybody shut down, stop, back away. We're calling an electrician to come and fix this because we ain't playing this. At 600 volt power supplies, it will arc across and get you. You don't have to touch it, you just have to get careless enough to get too close and it'll get you. And it was, that was probably one of the most frightening things I'd ever seen. Oh, hey, when it comes to high voltage, you ain't going to find a bigger coward than I am. Low voltage stuff, I'm fine. Because the worst I'm going to do is blow up a few $1,000s worth of electronics. But that high voltage stuff, nope. Get out the paintbrush and just slap a big yellow stripe down my back because I ain't playing that. Speaking of which, power in household circuits. They're telling us about fuses and multi-breakers or circuit breakers. You understand how a circuit breaker works? Basically, it's a bimetal strip. And it's, mechanically it's tenuous, but the dimension of the strip changes because of the heating, overheating. It curls up and it's a spring-loaded thing that's under tension and it pops. Yeah, I guess what you need to know from this is the amount of power. The total amount of power dissipated in a circuit is simply the sum of all of the power that's dissipated. And this is true in household circuits where everything's in parallel. You'd have to, Y'all are familiar with parallel and series circuits, right? Okay, then I can't imagine this is going to give y'all trouble. You would have to determine how much current the breaker can handle and how many of the loads can add together to get the current up to it. But if you've got multiple loads in parallel, then every time you you turn on another one of those loads, that current is added to the total current drawn on the circuit. And the breakers are set to kick off at a certain current flow. But whether we're talking about household circuits or printed circuit boards, the power that is dissipated is always the sum of the power that's dissipated in each component in the circuit. Doesn't matter if the resistors are in series or if they're in parallel. However much power they're dissipating, you add them all up, and that gives you the total power in the whole circuit. And a dangerous extension cord draws too much current. And then we get to alternating current, and we're going to get into root mean squares and all that. How many of y'all have y'all done the derivation of you've all done AC voltage, right? And how you have to measure, you can't measure the average, you have to measure the root mean square. Okay, have y'all been through the derivations mathematically, why you have to do? No? Oh, well, buckle your seatbelts and get ready for Wednesday. We'll go through that Wednesday. You're going to find what you will learn on Wednesday is that there is no such thing as the RMS power. You can talk about RMS voltage and you can talk about RMS current, but you cannot talk there's no point in even talking about RMS power. Power is power is the power. And oh yeah, quick question. How many of you have circuit simulation software on your laptop computers or tablets? I don't know, whatever y'all use to simulate simulate circuits. You set up a voltage source and a load and resistors and switches, and you turn them on and it tells you how much current is flowing in each branch. And you have that? Spencer, do you? Do y'all? Do you? Okay, those of you who have it, bring it with you. Make sure you bring it in the lab on Thursday. And those of you who don't worry about it. We'll get these old. Oh no, somebody turned off that Mac. I wonder if it's going to turn back on now. Well, I'll worry about that when I worry about it. But we'll get at least one of them up and running, and y'all can use some software that's on there. I'll show you how to use it. That's going to be the lab. We're going to be doing circuits. So, see y'all then. Have a good day. And if you have any questions about homework or whatever, you know where to find me. Anybody not sign in? Ooh. You betcha. See you on Wednesday. What you think, Dustin? Gonna make it?